Okay, we're going to take a look at just tracing a recursive method in a binary tree to kind of help you understand what's going on when you use recursion. For the most part, I tend not to think about it in a lot of depth. Like I understand what the process is, and once you get used to using it, you just use recursion and you just kind of know from experience that it's going to work. But a natural question is like, why exactly does it work? Because sometimes you've got a method and it seems too short and too simple to actually be the solution to a problem. And so you might wonder, where is the actual work happening? How is the method actually accomplishing the task it's supposed to accomplish? So I'm going to show you that here briefly. I will try to make this short, but hopefully in going through this, you will look and get a better understanding of why it works, and then mostly just kind of learn to use it when you need it. And if you need to, you can always dig down and do this kind of analysis. But for the most part, if you know that this is how it works, you can just write your code and trust that it's going to work and everything's going to be fine. So the example I'm going to use here is finding the sum of the nodes in a binary tree. So I've got a binary node class over here, and in this binary node class, I've got data and then a left and right left and right child references. So for example, in this root node here, the data is 10, and then the left node and the right node are here. And we've also got this method here. We want to look in particular, this is why we're doing this, at a method whose job it is to compute the sum of all the nodes. And when you look at this method, you can kind of see what it does. It says, if I want to, first let me explain it in terms of the tree itself. If I want to find the sum of all of the tree, I can do that by finding the sum of the left side of the tree, so the left subtree, and the sum of the nodes in the right subtree, and get those two, and then add in the data itself. And so you can kind of see that in my code, those three pieces. You can see that I begin with getting the data itself. I'll say I know that's part of my answer, so this data is just the data in that node. And then you can see here I say if there's a left subtree and if there's a right subtree, then call left.sum if there's a left subtree and right.sum if there's a right subtree. And this is where the recursion happens. So I've got a method called sum inside my binary node class, and then it's going to possibly call sum in the left and right subtrees, if those subtrees exist. And in this case, since I'm computing a sum, I've got this result variable, and I am going to, if there is a left sum, I'm going to add it onto result. Same thing with the right, add it on, and then I'm going to return it. But it doesn't seem like there's a whole lot going on here. I mean, really, there's just 1, 2, 3, 4 lines of code that are supposed to go through and compute all, like the sum of all the numbers in all the nodes. So let's see how that works. The idea here is if I want to compute the sum of all the nodes in this tree, then I'm going to say root.sum. And so I'm going to put my sum method over here next to root so that we can see what's going on here. So what happens here is I am in the sum method inside this root node, and the first line of code says I'm going to assign the data to result. Well, in this case, the data in the node is 10, and so let's make data have the value of 10, okay? Now I go to the next line of code, and it says if the left is not equal to null, then make a recursive call to left.sum. So that's what we're going to do here, is we're going to go to compute left.sum. Now we're in a sum method right now, and this sum method says I need the result from left.sum before I can continue. So what happens here is this sum method, the sum method in the root is kind of put on hold. It's put on pause. We say it's put on the program stack, but it's paused here while it waits for left.sum to do its work. So now I'm in left.sum even though the roots, this one's sum hasn't finished yet. And once I get an answer to this, like once this method is done, I would then just send my result back up here because this is the method that called for it. So, all right, now I've paused the one sum method. I'm in this new sum method, and it says the result for sum in this node is going to be the data. So I'm going to change that to 11. And then I get to the next line, and it says if left is not equal to null, then I'm going to need to call left.sum. And once again, this is another recursive call. So just like before when we put a sum method on hold, now we have two sum methods on hold. We just now put this one on hold, and we have this one on hold. So this one is on hold, the one next to the 11, because it's waiting for an answer from here. Now, once this one gives back an answer, it can send it back up to this method and it can finish its work. And then once it gets its answer, it sends it back up here to that one. But let's work our way through this sum. So now we're doing the sum of this node. And so I go through, and the first line of code says result equals data. Well, that's 7. And then it says if left is not equal to null, well, left is null. There's no left child or right child. So nothing is actually going to happen here because both sides are null. What that means is I'm just going to return the result 7 because there was no recursion to do. And this is often what we mean by a base case when we do recursion. It's like eventually the code is going to stop. It's going to get to a point where no more recursion is needed. So now that the method is done, its job is to send its result back up to the method that asked for it. So remember, we were doing this because 11 asked for left.sum. So we're going to pass the 7 up to here. And that's what we got back from left.sum was this 7. And then that is being added on to result. So result is gone from 11 to now it's 18. And now we are done with this first if statement here. And the first if statement is done. The next if statement says if right is not equal to null. But in this case, in the 11 node, there is no right tree, and so we won't have to do this line of code at all. It just gets skipped, which means we're down here now on the return. We have finished this method, and the answer is 18. Now, why did we calculate this sum? It's because this method up here requested that we calculate it. So we have completed calculating the sum starting at the left subtree. We can pass this 18 up to the method that asked for it. So that brings us back to the original method, and we got back an 18. And that means that's being added to result. So now result is 28. And we're done with that if statement. So we move to the next if statement. And in this case, right is not equal to null. And that means we're going to make a recursive call to compute the right sum. So the recursion begins again. That means, again, that this method that we're in right now in the root has to pause again while it goes on to the next, makes its recursive call. So it's calling right.sum. That means we're going to go down to this method here and compute its sum. And once again, we can see up here that the sum method in the root node is on pause. So it's time to compute the sum of this node that contains 9. So the data will be 9. And now it makes a recursive call left.sum. That means that this is also going to be put on hold while we compute left.sum. So I'm to a leaf node, just like the 7 before. The result is going to be 15. And in this case, this node, this 15 node, does not have a left or right child. So these would be skipped, and 15 will be returned. And where is that 15 returned to? It's returned to the method that asked for left.sum. So we take that 15 and we send it up here for the result of left.sum. And that means result is going to be increased by that. So now it's 24. And we are done with if this side. Now we need to check this side. Well, this side also has a subtree, and so we're going to have to make another recursive call to right.sum. So that's once again going to put this sum method on hold. So we have two sum methods on hold. We would say that there's two methods on the program stack named sum. And so now we're computing the sum of this 8 node. And in this case, the result is going to be 8. It does not have a left or right child, so it's a base case. That means we're going to return 8 to the method that asked for it. This method asked for right.sum, and so now we can send that 8 up here for right.sum. And that is going to be added on to the result, so that brings this up to 32. And now we've reached the end of this method, which means we're going to return that 32 up here to the method that asked for it. And so we return that 32. That was what we got for right.sum. And that's being added on to results, so the 28 is going to become 60. And now we've reached the end of the original sum method. We return 60, and that is the answer that we were looking for, is 60. So you can see that all of the numbers, 10, 11, 7, 9, 15, and 8, got added together at various times. If you really look to see the order that things happened in, we first started at the 10 and then moved to the 11, which called the 7. When that was done, it went back up here and returned an answer. When that was done, it returned here. But then we went to the right, and then we went to the left, and then we went back up to here, and then we did the right again, and then we went back up to here to return it, and then we ended up back up here returning the method. So it looks like kind of a mess there, but if you really trace through one line at a time, and you put those methods on pause when they make their recursive calls, it kind of makes sense where these numbers are coming from and when those things actually happen. So do you have to remember all of this all the time when you're working with recursion? Definitely not. But if you can think this way and you understand where it's coming from, then you can just trust recursion is going to work. And then anytime you distrust it, you can get out paper and pencil and do this kind of analysis if you need to. So that's it.